Okay guys, so today we're going to look at the concept of enthalpy. We're going to relate it to internal energy. And we're going to look at the specific heats, Cp and Cv. All right, so be careful here because this is conceptually, it's not difficult, but this is important, okay, to understand this, because you're going to see that once we move to the different type of system, you're going to have to recognize if you are dealing with Cp or Cv, but if you understand where it comes from, it's easier, okay? So we said that in this part of the chapter, we are dealing just with a closed system. And we said the two types of closed system we have is like a box, where you know the amount of mass inside. So this is your system. The amount of mass, let's say, will be constant over here. And imagine that into your system you add heat, okay? So in this case, what is constant? In this case, you see that the volume is constant. So in this case, you have to deal with Cv. Now, the other case that we have been dealing with is the piston cylinder type of system, which basically is, you have this, and this is our system over here inside. And again, the mass could be constant, and let's say that we add heat. But the other day we finished saying what? If this is free to move, what is constant in this type of system? The pressure is constant. So in this case, you have to use C sub P. I mean, you don't have to, but it will be easy, okay? You can actually use C sub V, but it will be different. Okay, so if we use the first principle of thermodynamics, that will be what? Q minus work equal, let's say, neglecting kinetic and potential energy. What do we have? This should be equal to the change in internal energy. All right? So let's say neglecting kinetic and potential energy. All right? Neglected, 0. So again, we assume this will be, we are going again assuming the ideal gas relation. So is it any work done in that system? There is no work done, so work equal to 0, which means that then the amount of heat will be equal to the change in internal energy, which for an ideal substance we know will be equal to what? M C sub V change in temperature. Yeah, I hope you remember that from the previous class. For an ideal substance, you can say this is equivalent to mCv delta T. All right. Now let us do the same thing for the piston. So for the piston, we have the first principle of thermodynamics, Q minus work equal again to change in internal energy. So now, is there any work done in the system? Yes, the piston is doing work, no? And if you remember, the definition of work done by the piston is Q minus, so this is work done by piston was equal to PDV, pressure times volume. And if it is constant pressure, remember we have three cases, constant pressure, and then 2 for polytropic, no? But if it was constant pressure, it was equal to P V final times V final minus V initial, which is basically what we have over here. And this will be equal to the change in internal energy. So in this case, on the second case, you can see that the amount of heat added will be equal to the change in internal energy plus the work done by the pressure. Okay, and this is what is new. This quantity here is called delta H, okay, which is the change in enthalpy. I will give some more detail on there, okay? So if you want, let's come over here. H equal to delta U plus PDV. So this is the enthalpy. So what is the definition of the enthalpy? Is change in internal energy plus work done by constant pressure. And what's important here is constant, okay? Because if it's a polytropic process, it doesn't work. But now, when I go here, what's important is that to realize that for an ideal gas, for an ideal substance, this is proportional to what? To the change in enthalpy, which is equal to M Cp delta T. Okay, so you see over here that the two expressions, the amount of heat that you need to put on this one is proportional to the internal energy. And this is the important part that you remember. The internal energy is always related to the C sub V. Okay? In this case, because the pressure is constant, the amount of heat you need to put inside is equal to the amount of internal energy plus the work done by the pressure. All right? That quantity here is also called the enthalpy. So every time you have to deal with the enthalpy, you need to deal with the C sub P. Okay? All right? And it's starting to get confusing. All right, over here, now I'm going to do one thing. I'm going to put a little note. It's not that important, but just in case you are picky about the notes. All right, so definition of enthalpy is U plus PV, no? Let's say internal energy plus PV. So if we do the derivative of this, what would that be? Will be du, and now the derivative of this will be, if this is uv, will be u prime v plus uv prime, no? So it should be equal to pdv plus v dp. All right. However, what do we know about this type of system? What is constant? So if P is constant, what happened? This is zero, no? And you see that for a constant process, we end up again to the same expression that we had initially here, that the change of entropy at constant pressure is equal to change in internal energy plus work done by the pressure. But this is only valid when P is constant. All right? But again, I mean, we did it here, but this shows you that also you can do it by math, not the proof. All right, so again, really important here to memorize that, and this is memorizing, is that if you deal with use, you need to deal with C sub V's. If you deal with H, you need to deal with C sub P. Okay? Okay, now because of the problem the other day, which was involving the specific heat relations, I'm going to give you the specific heat relations now. Okay, so specific heat relations. Which again, I'm not a fan of all this stuff because they don't add anything to the understanding and they just complicate everything. It's just notation. Okay, the previous part, this one is understanding, so this is important. This part is, I mean, since the exams will be take home, you're never gonna have a problem. But here we have to deal with CPs and the CVs. So let's see, we have the constant K on the book, which is the gas constant, and for you in later classes in aerospace, we have the letter gamma, okay? By definition, is equal to the change in enthalpy divided by the change in internal energy. Even though people do not really recognize that, so this should be equal to what? M Cp delta T divided by M C sub V delta T. So you see that this gives you right away that the gas constant really is equal to what? Cp over Cv. Oops, the CV doesn't cancel, okay? I mean, it's easy to see. So basically, what is the definition of K? K is the ratio at which, let's say, what would be the amount of heat you need to put into a system that is a piston cylinder assembly, and you divide the amount of heat you put into the amount of heat you need to put into that system at a constant volume, okay? Johnny, the value to get the CV is how much energy you need to put to raise, I think is 1 kilogram of substance or 1 gram of substance to raise it in by 1 degree in 1 second or something like that, or 1 minute, okay? So it's a ratio, no? That's what they call specific heat. Amount of heat you need to provide for constant pressure, constant volume, okay, to raise 1 degree Celsius. All right, so now this was another relation, is that Cp, and this one I need to look at it because I don't know it, so Cp is related to the Cv with Cv plus R bar. R bar over M, which is a universal gas constant, so this is the same thing as saying Cv plus R. Okay, see, I always don't know those R's, and so over here, let's say we keep the relation Cp will be equal to C sub V plus R.
Did you say R is the gas constant?
Okay, so from these two relations, you can rewrite different relations, which is, for example, K equals CP over CV.
And then there's from last time, R bar is R divided by.
So, okay, so let's make sure that's clear. Because I tell you always Zoom recording, I maybe correct this one. So let's try to be consistent with the notes. If you go to the page 19 on the class notes, I did define at that time that R bar is the gas constant divided by the molar mass. So R is the universal gas constant. Okay, no R bar. So that means maybe we need to change this stuff over here. So this will be, so we need to change that a little bit. This will be then R, and this should be R bar, no? There we go. Thank you for that. So let's be clear over here. R is the universal gas constant. Okay, I didn't put it clear because I'm running out of space. All right, so this will be equal to C sub V plus R bar divided by C sub V. Okay, so doing basic algebra, this is equal to K C sub V equal to C sub V plus R. I can factor out the C sub V. So C sub V of K minus 1. I keep forgetting the bar. R bar equal to R bar. So in that case, we're going to have that C sub V is equal to R bar K minus 1. So basically that means that if somebody gives you the gas constant, okay, K or gamma, which is the ratio of the specific heats, you can find what is C sub V, okay, if you have to deal with a constant volume. Now, what happens if you need C sub P? So we can do the same thing. You use the same relation, K equal to C sub P over C sub V, but you can use this relation now. You can just write that K, so this will be CV C sub V plus R bar divided by to do that. I mean, maybe I can do the opposite. I mean, I need a C sub P, so why am I replacing this one? Will be, sorry, let's do this. Will be C sub P. I mean, I can just replace this equation here, R bar divided by K minus 1. Okay, so let's do one more step. So it would be K equal to C sub P, K minus 1 divided by R bar, which will give you that CP is equal to R bar K divided by K minus 1. So again, these relations, you don't need to memorize. I mean, write them somewhere because this is, I think it's a waste of time, okay? Doesn't add anything to the understanding and just complicates everything. All right, so in today's class, what's important is this part over here. So let's try to do an example or a problem about this part over here. This is just for that you have the data. I mean, there you have the equations. Okay, so the exercise or problem is the following one. Let's say you have a piston cylinder assembly. So that means that the mass is constant, and you know that it's nothing apply anything, means that the pressure will be constant. So you are adding heat, and you know that the initial temperature, so the initial temperature is 50 degrees Celsius. You add the heat, and at the end, T2 is equal to 100 degrees Celsius. And you are dealing with an ideal gas. Okay, and that this is an ideal gas. Okay, so the question is determine the amount of heat per unit mass that you need to provide, okay? And everything is going to be symbolic, really. Just put, I don't like put the values. I put these values, but I'm not going to use them. Okay, so the way, personally, I would like you to see solving this problem in two different ways, or to realize, is to do what? First thing would be to apply the first principle of thermodynamics, which is what? Q minus work equal to change in energy, okay? Where we know that the change in energy is equal to the change in internal energy plus the change in potential energy plus the change in kinetic energy. In this case, we know that we can neglect the potential energy and the kinetic energy. So basically we have that Q minus work equal to change in internal energy. And basically, what is the work? We know by definition that work is P dV, which for constant pressure was equal to P dV, no? P d final minus V initial. So this is for constant pressure. This is the same as in this is P V2 minus V1, it's the same. Okay, so I can rewrite this equation as what? Q minus P dV equal to change in internal energy, okay? So now I can just put for the assumption for an ideal gas, for an ideal gas, we know that the change in entire energy will be proportional to M CV change in temperature dt, no? That's what we just saw. U will be related to CV. U related to CV. So we can rewrite the equation Q minus PDV equal to M CV dt. So we need to solve for Q. So that will mean that Q over M will be equal to P dV over M plus CV dt. What is volume over mass? Specific volume. Do you remember? In thermodynamics, everything that is divided by mass, we call it specific. So we could say that this will be equal to Q over M will be equal to PV, P delta V plus CV dt, or if I expand it to make it more clear, will be Q over M is equal to P V2 minus V1 plus CV T2 minus T1. Okay, so this will mean what? That we solve this equation in function of CV, that we use basically the relation CV that is for closed. But what do you know? We have a piston, we should be able to use which constant? CP, no? So basically what we did here is use this equation here, delta U. So we should be able to rewrite it under this form. So let's see if we are able to rewrite it under this form with the equations that we have. All right, so let's go to the next page. Let me rewrite the equation. We have Q over M equal to P V2 minus V1 plus CV T2 minus T1. Okay? But now we can say, using ideal gas relation, and here I'm going to have to be careful again with the notation, so let's go to the page 19 of the notes. Let's see how we define it. So for the specific, we say PV equal to the R bar T, okay, for the specific volumes. All right. So we're gonna have PV equal R bar T. So from this equation, let's see, what is the one that I want to eliminate? Will be the V's, because we want everything. So this will give you that V is equal to R bar T divided by P. But remember that P is constant. So we do that and we rewrite the above equation. What do we have? Q over M will be equal to what? So we have P is unchanged, but V will become what? R bar over T, and we can change the V2 minus V1 by T2 minus T1. Did you see what I did over here? Okay, I replaced this V2 minus V1 by R bar over T divided by P, T2 minus T1, because these two are constant, no? P is constant and R is a constant. So you have to write this one, and these ones remain unchanged, plus CV, T2 minus T1. Here you see that you can cancel the pressures. You have Q over M by now equal to R bar T2 minus T1 plus C sub V T2 minus T1, which is equal to Q over M of C sub V plus R bar factor of T2 minus T1 and what I just gave you, that what is the definition of CP? CP is CV plus R bar, no? So this is really CP over here. So at the end you see that this is also equal to Q sub M equal to CP T2 minus T1. And really this should be proportional to what? If you look at the first page, to the enthalpy, but which should be the enthalpy per unit mass, no? Which is the specific enthalpy that should be little h minus h little 1. Okay, so basically in this case, you see that you can solve this problem here using the CV, but if you use the CV, then you need to take into consideration the work done by the pressure. But if you use the CP, within the CP, you already have the definition of the work done by the pressure, no? Okay? So that's it. I mean, the concept is important, but important here that you recognize is that internal energy will always be related to the CV, and that enthalpy will always be related to the C sub P. That's really the important part that you need to recognize over here. All right, so somebody asked me to go and look at problem 237, so let's look at it. But again, it's going to be different data for everybody, or at least it should be, so I can just go through the procedure, no? Okay? So, so assignment 4, problem 2.037. So let's see if I can minimize this stuff here. Okay, I don't know if I'm going to be able to deal with this stuff here. All right, let me do the figure and then I think I can delete. So a composite plain wall consists of a 5-inch thin layer of insulation and a 0.75 layer of siding. Okay, so let's see if I do the figure. So let's say will be, this will be the insulation, where we know that the thickness is 5 inches. And what else do we know? K insulation is 0.029 BTUs hour feet, and I think the Ricans is dividing. Okay. And a 0.75 thick layer of siding, K sub S equal to 0.058. So let's say L sub S equal to 0.75 inches, K sub S equal to 0.058 BTUs hour foot Rankine. All right, so let's see. The inner temperature of the insulation is 67 degrees Fahrenheit. So let's say this should be, I put it in red. I have no idea if it's going to be hotter or cooler. So 67 degrees Fahrenheit. The outer temperature of the siding is 8 degrees Fahrenheit. So this will be 8. So T sub S equal to 8 degrees Fahrenheit. Okay. Determine at steady state the temperature at the interface of the two layers in Fahrenheit and the rate of heat transfer of the wall in BTUs hour foot square. Okay, so we need to basically determine the temperature here. That would be, let's say, T wall, okay, over here. Maybe put it over here, put it a little bit down. All right. So basically what it means that we're going to go through this line, oops, this way here and then this way, okay, for the different materials. So we need to find TW in Fahrenheit and Q sub A, because I think it's BTUs per hour foot square. Okay. So for me, you see, is 12.12 degrees Fahrenheit, but let's see what would that be. All right, so again, here maybe it will help if I sketch what will be Q. So this is the heat transfer, no? So what do we know about the heat transfer? I think it's what we discussed last time. With the total heat going through the wall, will it be equal to the amount of heat going through the insulation plus the amount of heat going through the siding? No, it's the same, no? It will, all the heat will first go through the insulation and then all the heat will go through the siding, no? Okay? The only thing that the insulation is going to do is that it's going to slow it down. So what you can say is that Q insulation will be equal to the Q of the siding. And what type of heat transfer mode do we have? Conduction. And for conduction, what do we have? We had, we can use minus Ka dTdx, no? But I tell you, personally, I remove the minus sign and I tell you how I do it. So over here, what is the amount of heat going through the siding? It will be K insulation, no? I'll start from the left-hand side. The area would be the cross-sectional area. And now, what would be the temperature? Would be T of the insulation. I go left to right. Where do you go next? To the wall, divided by L of the insulation. Okay? Now, all the heat is going to go through the siding. So what are you going to have over here? Should be equal to K siding, same area. on which is exposed. All right. And now what should be the temperature? If I move if I go from left to right, will be T wall minus T sub S siding divided by L sub S. So if I just look at this equation here, what can you say? You can eliminate the A, and we know K insulation, yes. We know K siding, yes. We know T insulation, 67. Do we know T wall? No. But do we know TS? Yes. So what is the only unknown in that equation? T wall. So we can solve for T wall, no? Okay? So let's solve for T wall. What can I say? So basically, let me simplify this a little bit. Will be K sub I divided by L sub I, T sub I minus T wall, equal to K sub S divided by L sub S, T wall minus T sub S. So let's do some algebra. So we can write that, let's say T wall. So we move the T wall to the right. That will be equal to what? K sub S divided by L sub S plus K sub I divided by L sub I. And now I need to move then the other one to the left. And here we'll have K sub I, L sub I, T sub I plus K sub S, L sub S, T sub S. So I just need to solve for T wall. All right, so I'll solve for T wall over here on that equation. So this will give us that T wall will be equal to K sub I, L sub I, T sub I plus K sub S, L sub S, T sub S divided by K sub S, L sub S plus K sub I, L sub I. So now, what is the thing where you need to be careful? Probably is to, what is the values you're going to get, on what units you're going to take the temperatures, no? Yeah? So you need to take them in what? If you look at the units, the Ks are in Rankins, no? So you need to move these temperatures into Rankins. So maybe that's what the problem is, if you have any problem. So if you do the numerical application, give me the correct value. So we have T inside is 67 degrees Fahrenheit. What would that be in Rankins? Don't take the simplification of 460 because it might be picky, no? What is the transformation of 459 point something? Okay, so do 67 plus 459.7 for this one, whatever that gives you. And for the siding, you take 8. I can do that one. Fahrenheit will be 8 plus 459.7. So that would be 466. No, 467.7 Rankins, and that one I don't know. That would be what? 526.7 Rankins. Okay, and you know all the other values, no? So if you want, go ahead and check, okay, but if you want, I give you time to check, but in this case, for this data, I think you had to find 12.12 Fahrenheit. If you want, go ahead and check. Okay, guys, the other thing you need to change here before you do the calculation is the length. So make sure you put L sub S and L sub I into feet, okay, before doing the calculation. But again, guys, you see that here, make sure you don't round off the temperature because you might end up with an error that might be more than 2%. And personally, I don't care on the exams, but the system cares. And I think on the default, I put the maximum value, which is 9%, but I don't think it let you do it for every single problem. But if you look at the settings, I think I set up for the maximum value, and it's 9% that it lets you. That I don't think still is very big. Because let's say you solve this problem, if you are using this equation, you're not doing anything wrong. So why? Because you are doing some round off, it gives you the answer wrong. I don't think it's that important. Okay? So second part of the question, again, here I think is going to be, the accuracy is going to be even more crucial, is that we know that the amount of heat going through the insulation should be equal to the amount of heat going through the siding. So that means that in order to find Q over A, we can use either one of these two, no? Yeah? So let's say we're going to use the one that goes to the insulation. So part B, to find Q dot over A, we know that Q insulation, let's say, is equal to K insulation A, and just recopying the equation, T sub I minus T wall divided by L insulation. So here, from this one, I can find that Q dot insulation over A equal to K sub I over L sub I, T insulation minus T wall. So in this case, if you do a numerical application, make sure you know K sub I. How much was K sub I? 0.029. That's fine. You need to change the 5 inches into feet. So you have, let's see, 12 inches equal 1 foot. So you do the unit transformation. And then you know that T inside, you don't need to change the units. You just know the difference will be the same. And T wall, you just told me, is 12.116. So if you replace all this stuff, should give you in BTUs hour foot square. And if we didn't do anything wrong, but go ahead and check, to give you 3.82. Is that what you get? Okay. Okay, so it's good that somebody asked, because this way you see that on the homework they only ask you for the answer, but if this is in the exam, this is what I want to see. To me, when I be good in the exam, what do you think I will be looking for? I'll be looking, one, for the figure. No? The second equation I'll be looking for will be this one here, because that will show me that you understand that the amount of heat is the same one going through the insulation as the siding, no? Yeah? The other equation I'll be looking is this one. And this one or the other one, okay, for the siding. If I see those 3 equations or 4 equations, you will have 8 or 9 points out of 10, even if the numerical applications are wrong. What do you think you're going to get if I see the correct numerical applications and not the equations? Probably 2 or 3 points, no, out of 10. I don't care about numerical results. I care about equations. All right, so make sure you show me the work. Okay, let me just look at the problem very quick, and you correct me. Maybe you can give me, so 3076. So when I read this problem, let's see what they say. So air contained in a piston cylinder assembly. So I will do the figure of a piston cylinder. I'm not showing you, but I'll show you in a minute. So the figure I will do is this one here. All right. And now I'll keep adding data on it. So let's see what I know. They say initially at 2 bars, so I will put under P1 equals 2 bars. T1 equals 200 Kelvin. And V1 equal 1 liter. Undergoes a process to a final state where the pressure is 6 bars. So then to the right hand side of it, I will put P2 equals 6 bars. Let me show you what I'm doing. I mean, you're gonna put initially this, okay, to the right. And the volume is 2 liters, so V2 equals 2 liters. During the process, the pressure-volume relationship is linear. Okay, assume the ideal gas model for the air, determine the work and the heat transfer, each in kilojoules. So assuming ideal gas, I will put here ideal gas. We need to determine the work, so W and the heat transfer. And they tell you the relation is linear. So, but here, and they tell you that the relation between the pressure and the volume is linear, no? Is that what they say? So what does that mean? I think the important part is over here. So basically we have here P, and this is V. Let's see what you have. P1 equal to 1. So let's say 2 and 1. Let's say this will be here. 2, 1, and we go to 2, 6, no? So let's say it will be 6 and this will be 2. So they say the relation is linear. Okay, so here, so you had a question about what, Q? Or how to find Q or the work?
Yeah, how to find Q.
Okay, so here there is one, I would do this either 2 ways. Either by understanding is that what is the work? Is the area under the curve, no? So you could do it that way, which would be perfectly fine. Or what can you do? You can go and try to find the equation of the line, no? Yeah, and then you just need to integrate it. So probably let's do the mathematical one. All right, so let's see what happened. So the fastest one probably just to find the area under the curve. But let's go find the equation of the line. So find equation of line. So let's see. In order to find the equation of the line, you need to know two things, no? 2 points. Correct? So right, let's do it mathematically and then we change the variable. This is what will be the equation of this line, will be of the form ax plus b, no? Or in our case, it will be equal to what? Of the form p equal to a v plus b, no? Yeah? So we need to know 2 points. What are 2 points that we know? So the first one could be equal to y is equal to p, so will be, let me do it under. So 2 should be equal to what? So a times 1, no? So a plus b. And the third one, 6, will be equal to what? 2a plus b. All right, so I mean, let me do this a bit quick so we have time to finish it up. One quick way to finish this would be to do what? If I rest this, subtract these two equations, what do you get? Minus 4 equal to minus a, because this b will cancel out. So you will get that right from here, you will get that a is equal to 4, no? And what will you have? And b will be equal to what? To be just be equal to 2 minus a, which would mean that b will be equal to minus 2. So that the equation of the line will be p equal to 4v minus 2. Let's go and check. If v equal 1, 4 minus 2, 2, no? If v equal 2, 8 minus 2, 6. All right? So now, by definition, what is the work? Is equal to the integral of p dv. You see, it's a lot faster to do it geometrically, but this will be equal to what? Integral of 4v minus 2 dv. So the work will be equal to the integral of 4v squared over 2 minus 2v between 1 and 2. So this will give you what? So this should give you, it should be 4 times 2, 8. 8 minus 4, 4. Should be, so 4 over here for the 2. Is that correct or no? So 4 minus 2 minus 0, no? So basically it should be 4 kilojoules. So now maybe I see what could be the problem on part B. So I should be page, let's see, 45, 46. Let's see how, okay, so I see what the problem is in part B. Part B can be maybe a little bit tricky. I don't know how you have done it, but so for part B to find Q, what do we know? You need to use the first principle of thermodynamics, that will be Q minus work equal change in internal energy. Okay, so basically is what we have done today. So Q will be equal to what? Delta U plus the work done by the pressure. So you see, you can do it both ways here. So what can you say? So Q for an ideal gas, what do you know? You could say that Q is equal to M to CV. Oh, but we first need to find M, no? So sorry, it will be M over here. So I'll do it a bit quick, okay? It's the time MCV plus the value of the work that we just obtained. All right? Or actually, what could you do? You could say that this will be equal to MCP T2 minus T1. Okay, I'm going a bit fast now. If you get a little bit lost, don't worry about it. How would you find CV or CP? You can go to the tables, I don't remember which one, but you take T at T average, that would be what? T1 plus, we don't know T2? Okay. You have to solve for that first. Okay, you will take T1 over T2 divided by 2. And then how can you solve for the mass? You can use the ideal gas relation, PV equal nRT, no? So PV equal nRT, I don't know if it's R bar or no R bar now. I completely guess. I never know, but basically, you know, on state 1, you know the temperature, you know the pressure, then you know the volume. If you know it's air, you can find the molar mass, which is 28.97, and you can solve for the mass, no? Yeah, where N would be mass per molar mass. So from here you get M. And now and T2, you can also get it from the ideal gas relation, no? Yeah, you know, so for this one you use P1, P1, T1, and from P2, V2 equal nRT2, you can solve for T2. Okay? But again, and now CP or CV, you can find it from the average value. So if you use this one, you're going to have to put the value of the work. If you just look at the CV, it should give you the same answer. That way you can check, okay? So I hope that helps.
Yeah, I forgot to take the average of T, so I tried all the different values and none of them worked. So I ended up using the table to find the actual value of T and just do like mass times.
Okay. Yeah, if you go to the, yeah, and that would be more accurate actually. But yeah, but if you do the average, maybe it should give you the correct answer. The molar mass, where is it?
Yeah.
No, you're gonna have to go look for the table. So they tell you the substance is air. If you know it's air, I think it's on table 1, A1. And if I remember properly, it's 28.97. Yeah, you're welcome. All right, so I'm gonna stop the recording.